Okay, so we're going to take a look at some electric circuit questions. One we've got here is, it says, the compressor on an air conditioner draws 59.3 amp when it starts up. The start time is about 0.317 seconds, about 300 milliseconds or so. How much charge passes a cross-sectional area of the circuit in this time? It's a little tricky in what it means, but let's take a look overall at what's being said. We have an air conditioner unit. So the outside unit. And we're talking about the compressor, which is actually a small compression motor over here. Now, one thing that I do want to bring up is, if you're in the Gen class, a little while back we talked about thermodynamics, and one of the things that we looked at was the refrigeration cycle. You can go back and check your notes, and what we're actually talking about is the section of this in which we have an adiabatic compression. That's pretty much the most that I'm going to talk about it, just because when you end up with problems like this, everything that we've done in physics has been built around real-world applications, which means this isn't just a bunch of words strung together. This is actually what happens when your air conditioning kicks on. Now, 60 amp, which is a randomly generated number that they have in here, but even still, there's a large amount of current that is drawn right when you start big objects like that, say the compressor. There are times when you might see the lights flicker when you turn on a large appliance, something like an air conditioner, or when you turn on, say, a microwave or a clothes dryer, that sort of thing. Those things usually take a lot of power, and a lot of times when you first turn them on, it'll affect other parts of the circuit. Regardless, you don't need to worry about this. You can also look at this and simply say, okay, they're words. We've got an object, a circuit, that is pulling a current of 59.3 amp. Now here's where I'm going to bring in some of the stuff that we've talked about in class. It's worth remembering that an amp, 59.3, is actually a coulomb per second. Now, the SI unit is amp, but it's a lot like Newton. We have a name for it, but it still breaks down into a kilogram meter per second squared. We talked about this in class where I told you to imagine that current was watching one point and how many charges go by it in a time. In this case, in 1 second. How many coulombs go by? In our case, nearly 60 coulombs go by 1 point in 1 second. That's a ridiculous amount of charge. So much so that I don't think that this number is entirely realistic, though I could be wrong. I'm not a technician. So, that being said, this is where that line comes back in. How much charge passes a cross-sectional area of the circuit in this time? They're asking how many charges go by. Well, in 1 second, we would have 59.3 coulombs that would go through. That's what the amp actually means. However, that would be 1 second. We don't actually have a complete second. In this case, what you can look at is this. An equation that would describe this is your current is equal to a charge divided by time. So if you want the charge, we need to get rid of the time. Well, we can do that by multiplying both sides by the time. And we end up with the following. Q, our charge, will be equal to our current, which is in coulombs per second, times the time in seconds. We'll get the following. Q equals 59.3 coulombs per second. This is an amp. Times a time of 0.317 seconds. The seconds cancel out and we are left with coulombs. This will tell us how much charge goes by that point. Now I know we didn't necessarily do this exactly in class, but this is one of the things that I want you all to understand is the relationships between what we're describing with current. It talks about how much charge is going by. And we did do something very similar to this, where we used power and energy and time to find out how to work with a, well, kilowatt hour. That was a strange unit. We also have kind of a strange approach on this, but it's the same idea. How much of something we have in a given time, we multiply that by the time, and that will give us our result. 59.3 times 0.317, if you prefer, The amount of charge that goes by should be 18.80 coulomb. Still a very large amount of charge. I think that's a little high, but again, not a technician. I'm checking the results, and that is exactly what they would expect. Again, the key thing on this is to keep in mind that the current describes how much charge is going by one given point in a given time period. In this case, we have 59.3 amp, which means we have 59.3 coulombs every second. We don't have a full second, we only have about a third of a second, so we end up with about a third of this value. And one final thing, even though it's not terribly important, this is a real life thing that we've talked about before, though I'm not certain the numbers are exact.